Previously in the complete creation.
You remember those pig and elephant fossils that were found scattered throughout the layers above and below the KBS Tuff? I'll let Lubenow explain it so eloquently. The pigs won. In the 10-year controversy over the dating of one of the most important human fossils ever discovered, the pigs won. The pigs won over the elephants. The pigs won over potassium-argon dating. The pigs won over argon-argon dating. The pigs won over fission-track dating. They won over paleomagnetism. The pigs took it all. But in reality, it wasn't the pigs that won, it was evolution that won. In the dating game, evolution always wins. Hello again, thank you for joining me in the next part of this series. We've been looking at the various radiometric dating methods used by old Earth advocates who adamantly claim that radiometric dating produces reliable, absolute ages. When it serves their purposes, they are just as quick to reject their own radio dating methods when the ages given don't line up with the evolution column. Carrying on with that theme, let's take a brief look at some other creative ways young Earth creationary scientists were able to scientifically determine geological dates. Dr. Robert Gentry became known for his work on pleochroic halos or radiohalos in the 70s. I highly recommend visiting his websites, either halos.com or halos.us, and checking out his book, Creation's Tiny Mystery. On his website, he has dozens of technical papers he has published on the topic available for viewing and download, and they are each a must-read. A radiohalo is radiation damage collected inside a substance, typically rocks, which has small clumps of a radioactive material inside it. The center is a microscopic clump of some radioactive isotope. Alpha radiation is emitted in all directions from the clump. And think of the alpha particle like a bullet being shot into some wood. It comes to a stop inside the wood, but the path the bullet took is a path of damage inside the wood. So inside a rock, you'll get these clumps of radioactive material, and the isotopes are firing alpha emissions in all directions, with each alpha particle leaving behind a trail of damage. Now, if you'll remember, some alpha particles are kicked out of the atom with more energy than other alpha particles. It depends on the parent element. Higher energy particles will, of course, travel farther in the rock before stopping. And so hundreds of millions of alpha particles being emitted in all directions from one center will leave behind a sphere of radiation damage surrounding the radiocenter. We can tell what the element is by the size of the sphere, because the size of the sphere is dictated by the energy of the alpha emissions. And the energy level tells us what element it is. We come along, slice the rock through the center of the sphere, and now we are looking at the cross section of the sphere with the radio center and the radio halos generated by radiation damage. Now, of course, that radioactive breakdown was a chain of parent-daughter elements. A parent element radioactively breaks down into a daughter element, which is often itself radioactive. So the daughter element breaks down as well into another daughter element, which is also radioactive. So here in this photograph, of a radio halo cross-section, you can see multiple rings of radiation damage, each ring with different diameters. You can identify which isotope made which ring by measuring the diameter of the halo. I mentioned that usually these rings are found in rock, but the rings will be formed in any solid containing radioactive materials. And Dr. Gentry documented a fascinating and very unusual case of radiohalos in coal. Now remember how coal is found. Typically it's wood or bark from trees that gets collected into thick layers by water, buried under sediments, and the weight of the overlying sediments compresses it while it's all heated in anaerobic conditions. The wood and bark turn to coal. And in one of his videos, Dr. Gentry and his son David show you an experiment where they basically made the first stage of coal in the lab in a few days. It doesn't take millions of years. They also show in that video actual footage of crude oil being formed by natural processes off the coast of California. Again, it doesn't take millions of years. It can be observed being formed today. And to top it all off, while you can get the video on DVD or even VHS, Dr. Gentry has made the video available for free streaming on his website, halos.com. I highly recommend you check it out. So Dr. Gentry took coal samples from multiple coal mines in Colorado, dated on the evolutionary column as Eocene, Jurassic, and Triassic. Notice the time span involved here using the ages given by the deep time advocates themselves. The Eocene samples would be 37 million years old and the Triassic would be 245 million years old. That's a time span of 208 million years. So Dr. Gentry did find some pleochroic halos in the coal samples, but get this, they've been squished. The radioactive materials were apparently in the water, which was soaked up by the plants, and thus the plants wound up with little clumps of radioactive dirt in the porous wood. The materials started breaking down radioactively, creating spheres of radiation damage within the wood, radiohalos. The woody material was then compressed during the process of turning it into coal, so compressed by the tremendous weight of sediments of what is now the rock record, and so the radiohalos were also squished and compressed. There is something significant to be noted here. There is only one ring of radiation damage. That narrows down the list to one of two possible isotopes, lead-210, which emits beta radiation and would not produce a radiohalo, but transmutates into polonium-210, which is the other possible isotope for this halo. Polonium-210 has a half-life of 138 days, quite short. It takes at least 500 million radioactive decays, alpha emissions, to make a visible halo. For some of the radiohalos, as you can see here, the story ends there. However, Dr. Gentry also found some squished radiohalos that had further radioactivity occurring after the compression event. There hasn't been much radioactivity since that compression event, so the radiohalo is quite faint. Oh, wait! We can now use this as a clock. We know how many alpha emissions it takes to form a radiohalo. We know the element that made the radiohalo, and we know the half-life of that element. So it becomes simple math, because we can estimate how many emissions have gone on by the density of the fission tracks and divide it up by how many emissions per year you would get from that isotope. This is, in effect, a unique form of fission track dating. I mean, a half-life of 138 days? Stop and think about that. How many radioactive emissions are you going to get in the minimum 37 million years? Obviously, you're going to get into the billions of emissions, and thus very dark radiohalos, which is not what we see. We see young radiohalos. Just as significant as the polonium radiohalos is what is not found. Radiohalos from other longer half-life isotopes like uranium. I mean, presumably, there was also uranium in the water soaked up by the wood as well. So where are the radiohalos from the other long half-life isotopes? Remember, this coal is alleged to be tens to hundreds of millions of years old. That is plenty of time for radioactivity to produce copious, very dark, old radiohalos from even long half-life isotopes. So, where are they? The combined evidence shows that all of the events associated with this coal happened very recently. The soaking up of the water with radioactive dirt particles in it, the compressing of the wood into coal, the time since the wood turned into coal. Dr. Gentry summed all of this up in his paper in the secular, peer-reviewed journal, Science. Such extraordinary values admit the possibility that both the initial uranium infiltration and coalification could possibly have occurred within the past several thousand years. Because they collected samples from the Jurassic, and Eocene deposits, this would represent an evolutionary time of 37 to 245 million years, 208 million years total. The flattened pleochroic halos and the radioactive decay that took place afterwards conclusively show us that, in fact, 208 million evolutionary years were actually all one event a few thousand years ago, exactly in line with the biblical account of a global flood and a few thousand years ago. Because we collapsed this huge chunk of the evolution column into one short time frame, we just collapsed this entire evolution column into one short time frame and event just a few thousand years ago. As profound as that evidence is, which I might mention has stood unrefuted for some 45 years now, Dr. Gentry was a nuclear physicist working within the defense industry and Oak Ridge National Labs for many years. His extensive work in a variety of fascinating nuclear physics research projects led him to researching zircon crystals. You remember them? Fission-track dating in zircon crystals was one of the dating methods used to try to date Skull 1470. So in his research for nuclear waste storage, Dr. Gentry studied radioisotopes within zircon crystals drilled from deep granites, and namely how much or how little radioisotopes would leach into or out of the crystals, especially at higher temperatures underground. He discovered by chance that there was a lot of helium in the zircon crystals. Well, let's go back a few lectures to our nuclear physics for home educators. Remember that alpha radiation is effectively a helium atom. So any alpha radioactivity produces helium. The helium atom is the second smallest atom known to mankind, and it's so small that it will readily leak through pretty much any substrate. It's also an inert gas, so it doesn't bond chemically with anything either. To help balloons retain their helium, you'll notice that they will often first put in a substance affectionately called balloon snot, for obvious reasons. The balloon snot actually coats the inside of the plastic or rubber of the balloon because the helium atom is so small that it will leak right through the rubber or plastic. This is why your helium balloon deflates over a very short time, and the balloon snot slows down the leakage to help keep your balloon afloat for a lot longer after your birthday party. So, if you have zircons in the basement rocks, assigned to the Precambrian and dated by deep time advocates as 1.5 billion years old. When the basement rocks were formed, they also formed these zircon crystals inside the basement rock granite. When the zircon crystals formed, they trapped radioactive uranium and thorium inside them. These radioisotopes then radioactively broke down over time, producing helium gas inside the zircons. Now, zircons are incredibly dense and tough crystals, almost as tough as diamonds. But the helium atom being so small, it still easily works its way through the crystal lattice. The gas diffuses out of the crystal. This was where Gentry first stumbled upon this surprise. There was way too much helium in the crystals. The helium is produced really slowly, but leaks out really fast. There should be a very small amount of helium retained inside the crystal. Instead, Gentry found that 50% or more of the radiogenic helium was retained inside the crystal. Before we go on, I wish to take a few steps back to the Skull 1470 fiasco. You remember that Hurford et al. Used fission-track dating on the zircon crystals in the 3.9 Tuff? They arrived at an age of 2.44 million years, which seemed to support Fitch et al.'s new age of the KBS Tuff at 2.4 million years. In 1977, G.A. Wagner of the Max Planck Institute for Physics in Germany wrote a letter to Nature magazine in response to Hurford et al.'s dating paper. Wagner cited his own paper in Nature magazine in 1975, where he took historic uranium glassware of known age and performed fission-track dating on the glassware. Now, uranium glassware was common from the 1800s through the 1900s, and it is literally uranium-infused glassware. The glass glows as a result, and yes, people would drink from said glasses and eat their supper from the uranium glass plates and bowls. But what Wagner did was really smart, because we know when the glassware was manufactured, and it was manufactured by melting the glass. So this was like turning the glass into lava and resetting the fission-track clock. Wagner could now go on, calibrate the fission-track dating method based on the fission tracks of this glassware, for which he knew the precise age of manufacture. But get a load of what he wrote in his letter about Hurford's work. Many fission-track specialists no longer use the decay constant 6.85 value, but now use the decay constant 8.46. There are good reasons for this preference. If this higher value for the decay constant is used, the fission-track age of the pumice and the KBS Tuff recalculates to 1.98 million years, which would lend support to the potassium argon age measured by Curtis et al. Hold up. This guy is saying the half-life of uranium-238 that Hurford et al. Used is no longer valid? And that the half-life they should have used was 19% higher? Whatever happened to constant? The half-life of an element is supposed to be a well-known, well-established number. I mean, that number even affects the safe and reliable operation of nuclear reactors, for crying out loud. You would think their numbers wouldn't be in disagreement by 19%, would you? Right? But wait for it. Here's what Hurford and team replied. Wagner has questioned our choice of a decay constant. When it is used in conjunction with the fission-track glass standards of the U.S. National Bureau of Standards, we get the best agreement for the potassium argon ages of coexisting minerals, and we use it for this reason. Translation. Well, if you use the fission-track glass standards here in the U.S., our dating of the KBS Tuff matches the dates obtained by Fitch-Miller and many others. So, a benchmark measurement, you would think, was solid in the scientific community. The determined half-life of probably the single most important radioactive element known to and used by mankind. You would think it's a number that would no longer be debated. But here we have experts in their field on two sides of the globe disagreeing about a number foundational to a number of multiple sciences, and they are in disagreement by 19%. Do you think you would pass your university exam for bridge design if your answers were 19% different than the professor's answers? But wait, it gets better. If you take a look at the 1989 reference from the International Union of Pure and Applied Chemistry, where they set the standards that scientists use for things like molecular weights, melting and boiling points, half-life, and decay constants, which apparently aren't that constant, because you can see here they've had a range of values for uranium-238 from the 6.85 that Hurford and team used, through to the 8.46 that Wagner said they should have used, through to the figure of 8.2 that the consortium arbitrarily decided should be the number everybody should use. But I mean, look at those numbers. Why use 8.2? Why not 11.8? Or why not 6.8? You can build a compelling argument for any of those decay constants, and you wind up with a half-life for uranium-238 of somewhere between 3.64 and 6.277 billion years. A half-life range of 173%. In 2017, geologist Dr. Andrew Snelling published a paper documenting the history of trying to determine the half-life of uranium-238 and 235, critical isotopes used in a plethora of purposes. He showed the research conducted over the previous 84 years, showing the variations in the constant, and ultimately saying, instead, the actual observable experimentally determined radioisotope decay data suggest that radioisotope decay rates have been decreasing in recent decades. In 2018, Lawrence Livermore Laboratories published a paper which seemed to fall in line exactly with what Dr. Snelling said, showing the historical half-life measurements of uranium-238. And please note that a lot of these guys are switching between decay constant and half-life. They are two different numbers that are directly proportional, and you can calculate them from one another. But as they explain in the abstract of their paper, there's really only been one published half-life for uranium-238 that everybody uses. And that's that one right there. Jaffe et al., who set a standard of 4.47 billion years in 1971. Notice that 47 years later, in the Parsons-Davis et al. Paper, they arrived at a value of 4.456 billion years, slightly lower than that standard. So with all this in mind, let us come back to the zircon crystals. After years of creationists rightfully criticizing the old Earth advocates for parroting their absolutely bankrupt deep-time dating methods, the old Earth advocates said, well, why don't you guys come up with your own dating methods then? So we did. An 8-year research project was launched, partnered by the Institute for Creation Research and the Creation Research Society. The project was titled Radioisotopes and the Age of the Earth, or RATE for short. You can now download both volumes of the reports for free from the ICR website here. One of those research projects tackled the helium diffusion from zircons. Now, it's pretty simple. For every uranium atom that breaks down into lead-206, you produce 8 helium atoms. So measure how much uranium has broken down into lead-206, multiply it by 8. You now calculate how much helium has been produced inside the crystal. Now measure how much helium has not leaked out. Measure the diffusion rate of how fast the helium is coming out of the crystal, and divide the amounts. Easy peasy lemon squeezy, you can now get an approximate age for the zircon. So that's exactly what Dr. Russell Humphreys and team did, but they took it one step farther. The deep time advocates claim that zircon is 1.5 billion years old. We creationists believe it is around 6,000 years old. Knowing how much helium was produced and how much helium is left in the crystal, Dr. Humphreys and team did the most powerful thing you could do in science. They made a prediction. If the zircon crystal is 1.5 billion years old, then the diffusion rate should be around here. If the zircon crystal is only 6,000 years old, then the diffusion rate should be around here. Please note that these two predictions are different by a factor of a whopping 100,000 times. So, in other words, this diffusion rate is 100,000 times faster than this diffusion rate. So the margin for error here is absolutely huge. You could be way off on your numbers and still be able to determine which model is the correct one, by how close the actual measurements plot to one of the predictions. So, when they actually measured the diffusion rates in extensive experiments conducted in the lab and plotted them on the graph, what did they get? Drum roll, please. They wound up with the actual measurements stunningly landing precisely on top of the young Earth predictions. Like, no contest. It's clear who the winner is here. So, don't forget, based on present-day decay rates, there has been 1.5 billion years worth of radioactivity in the crystal. But those decay rates are still hotly debated and appear to be measurably decreasing even today. So, from this research, we can conclude two things. One, that crystal and the granite basement rock of Earth matches exactly the scientific predictions if the Earth was only 6,000 years old. Two, the radioactive decay rates in the past were faster than they are today because you've had radioactivity on the order of billions of years by today's rates in a rock that we just demonstrated is only 6,000 years old. This is nothing less than stunning, but in the next lecture, we'll continue to explore these studies which actually all independently verify each other and tell the same story and in more detail. Thank you. I hope you'll join me again.
Coming up in the next Complete Creation.
So my good friend Brock Lee compiled all of the carbon-14 dates returned from all of these studies. Here Brock has kindly charted out all of these carbon-14 dates, and if you look closely, you'll see that all of the dinosaurs return carbon-14 ages, younger than the Neanderthal man fossil.
You can catch the entire series in a variety of ways. You can watch the show online at www.completecreation.org or www.genesisweek.com. You can also purchase the Complete Creation series in full high definition on Blu-ray or video on demand at completecreation.org. Or support the Miracle Channel with a monthly tax-deductible donation and access the entire Complete Creation series in high definition through Corco, Miracle Channel's video on demand service. We need your support to keep this program on the air. So please pray for us. And if you wish to financially support the program, Canadians can make a tax-deductible donation to Core Ottawa, Canada North Post Office Box 72075, Ottawa, Ontario, Canada, K2K2P4. Or you can make a donation via PayPal online at ianjuby.org/donations. And thank you for your support.